Welcome to Lecture 7, Light, a Particle. In our last lecture, we introduced the notion of light as an electromagnetic wave, talked about the electromagnetic spectrum, noted how it's broken into many different subsections, if you will, of which the visible spectrum is only a very small part, and began what we will continue today in our study of light. As I mentioned in prior lectures, the study of light is going to be important for us because almost everything that we observe in the study of astronomy comes to us in the form of light. And so our goal, not to beat a dead horse, but is to extract as much information as possible out of the light that we receive. So one of the challenges in understanding light is tied up in really the birth of modern physics in the form of quantum mechanics at the turn of the 20th century. And that has to do with an understanding of the nature of light itself. Is it a wave? Is it a particle? This was an argument that goes back hundreds of years, but it turns out that only in the advent of quantum mechanics and at the turn of the 20th century did physicists get to a point where they finally started to understand a little bit better what light is. And it turns out that that is encapsulated in a notion that we introduced last time called wave-particle duality, which is a fancy way of saying that light exhibits properties both of a particle and of a wave, and which types of properties we observe depend upon what type of experiment we're looking at. So in the last lecture, again, we introduced the concept, a lot of wave concepts, and looked at some cases in which light behaves like a wave. Today, we're going to look at the other side and talk about some specific instances in which light behaves very much like a particle. So let's dive in. So at a very high level, it turns out that describing light as a wave, as we did in our last lecture, tends to be most appropriate when we're describing how light travels through space. This is a very sort of very generic statement, and it's not. There will be counterexamples to this, but in general, when light is traveling through space, it is typically best or most effective to describe it or to understand it as traveling as a wave. In contrast, describing light as a particle, as we'll study today, tends to be the best way to understand light when it's interacting with atoms. And as you can see fairly quickly, we're going to be very necessarily concerned about both of these aspects of light because, again, as budding astronomers, in order to extract information about these astronomical objects, for example, stars, they're light years away from us, in order to understand what are the temperatures, what are the pressures, what are the attributes of these distant stars, we're going to have to understand both how light interacts with matter, because that is how the light is generated on these stars. But then once the light is generated, it has to travel through space to get to us. So that's why we really can't escape. If we want to do astronomy, we need to understand how light interacts with matter and how light travels through space. So without question, the penultimate example of a physics experiment in which light is most effectively described as a particle is something known as the photoelectric effect. And this is an experiment that was first performed sometime in the late 1800s, early 1900s, but it really became phenomenally famous thanks to Albert Einstein. And Einstein in 1905 wrote a paper in which he demonstrated basically he developed a theory that explained the experiments regarding the photoelectric effect at the time, and did so using a picture of light as a particle. And we'll talk in detail in the next several slides about what exactly the photoelectric effect is, what the experiments looked like, and how Einstein's description worked so well. But it turns out that this was the reason for Einstein's Nobel Prize as well, which he was awarded in 1921. And it really was a very big part of kickstarting the birth of quantum mechanics, which really defined the emergence of modern physics, which continues to today. So Albert Einstein could have, without question, won a handful of Nobel Prizes. He didn't. He only won one, despite having a number of sort of revolutionary theories that continue to hold sway today. But his one Nobel Prize was for his explanation of the photoelectric effect, which we'll now talk more about. So the photoelectric effect is very aptly named. You know, I've mentioned this notion that physicists are not very creative in their naming schemes, and why that's a good thing. Helps us remember what the heck we're talking about. The photoelectric effect can be broken down, right? Photo, as in photon or particle of light, and electric, as in electricity. So at a very high level, what's going to be happening here is that light is going to be giving rise to an electric current. And the way that happens is sort of schematically shown in this diagram. So what we're going to do is we're going to take a light source, and just to make it simpler, we're going to take a light source of a specified wavelength, specified color or frequency. So you can imagine this to be a laser. Wouldn't have to be, but just imagine that you have a single wavelength source, and you shine it on a piece of metal. And it turns out that we can choose lots of different metals. God has given us lots of different metals to choose from. But we're going to start with potassium just to make it concrete here. And so we're going to start off, imagine, and we're going to shine red light on the surface. And we're going to measure what's the current that's produced. And when you take light of a red color, and again, to make it concrete, let's say it's a 700 nanometer wavelength, which means a photon, a particle of light, and we'll talk more about this, but a photon is just the name for a particle of light. At 700 nanometers, each photon would have an energy of 1.77 electron volts. An electron volt is a unit of energy that is, it's very small by sort of comparison to what we interact with on a daily basis, but it's the right kind of unit to use when you're talking about energies of atomic energy levels, or photons, as we're going to be talking about today. So a 700 nanometer light wave photon has an energy of 1.77 electron volts, and you shine that on a piece of potassium metal, and you hook up, you know, an apparatus to an ammeter to measure the current, and it turns out the answer is 0. There's no current. Okay, so that's not a very interesting experiment, at least not yet. But now you say, well, okay, let's switch it out and let's use a green light source. And green has a little bit shorter wavelength, 550 nanometers. Correspondingly, the energy is a little bit higher at 2.25 electron volts. Again, that's energy per photon. And now, when you hook up that ammeter and you measure the current, turns out you do get a current. Okay? And what a current means is just there are electrons flowing. Okay? So we haven't gotten into the mechanism yet, but somehow when you shine green light on potassium metal, you get electrons flowing. Okay, somehow you have liberated some electrons from the potassium metal, from the potassium ion or atoms, and know that those electrons are flowing. Okay. Furthermore, if we just for good measure we say, well, okay, red didn't work, green works, let's try purple. Okay, well, purple has an even shorter wavelength of 400 nanometers. Has a photon energy of 3.1 electron volts, and in this case you also get a current, and so we'll talk about more details, but essentially what's happening here is that potassium requires 2 electron volts to eject an electron. Okay, if you want a technical term, that 2.0 electron volts is known as the work function of potassium, to make a connection with your reading. So what the work function tells you is how much energy do you need to does that photon need to have in order to knock an electron loose from its atom. Okay, and the answer is 2 electron volts. And so to understand what's happening here, the red photon only has 1.77 electron volts. That's just not enough energy to knock an electron free. So if you have a beam of red light that you're shining on this potassium metal, you can have gobs and gobs of these photons, but none of those photons has enough energy to knock an electron free, which means that you're not going to get any electrons freed, which means you're not going to get any current, right? If you want to have electrons flowing, generating an electric current, you need to free them first from their atoms, and these red photons just don't have enough energy to do that. In contrast, the green photons have 2.25 electron volts, which is more than the 2 electron volts they need. So essentially what's going to happen is 2 of those electron volts are going to be used to free the electrons, Okay, and now once you've freed it, you have a little bit of energy left, that 0.25 electron volts, and that's going to go into what's called the kinetic energy of the electron, which just means energy of motion. So that electron is going to now move away with some energy, with whatever energy is left, and that's what gives rise to the electric current. Finally, if we go to the case of the purple light, now you have even more energy in the photon. You have 3.1 electron volts, and so we take 2 of those electron volts are necessary to free the electron, and you've got 1.1 electron volts left over to carry that electron away. And so that electron will move away faster because there's more energy there. Okay, so we're going to talk more about this, but this right here is sort of the nuts and bolts summary of the photoelectric effect. It's really not a complicated effect now that we understand it. You know, this is the way that Einstein described it. But the key here is viewing the light as a particle, because to view it as a wave, it would have a completely different description. It would not explain the experimental observations. It wouldn't explain, well, why doesn't the red light create a current? Can't you just like hit it with enough of this red light, have the energy build up, and then eventually free an electron? And the answer is no, because we really need to view the light as lots of particles of light. And if those individual particles don't have enough energy to free an electron, then the electrons just won't be free. So we'll talk about this more in the slides to come. But this right here is sort of the nuts and bolts summary of the photoelectric effect, and it's going to be the foundation that we're going to build on in the next several slides. So there are a couple of terms that I want to either introduce or reintroduce that either will be new or we may have alluded to in the last lecture, or even in the context of viewing light as a wave. So the first here is the intensity. Okay, so the intensity of a light source or of any energy source is just the total energy in the beam. And if you want to be more technical, it's the energy per area per time. So for example, watts per square meter or something like that. So the important thing here is that no matter how intense you make the beam of red light, you never free any electrons. And this is an experiment that can be done easily. In fact, if you were to take Astronomy 30L, the lab class, then this is an experiment that you might do. It's an experiment that I've done in physics classes as well. And so you can just take this energy source, you can shine it at the potassium, and you can crank up the intensity. Just turn the knob, dial it from a weak beam to a very strong beam. But no matter how strong, how high the intensity is, you never get even one electron free. So why is this? Well, the answer is that, again, light is behaving as a particle in this case. And so the energy of each particle of light is completely determined by that light's frequency or wavelength. And so we've said already, but just to remind you, a particle of light is called a photon. And the energy of a photon is directly related to the frequency of that light, not to the intensity. Okay? So the intensity of the beam has nothing to do with the energy of the photon. The energy of the photon is completely determined by the frequency of the light. And fortunately for us, you know, again, this is not a class in advanced mathematics. We're not going to be doing a lot of plug and chug in terms of equations, but fortunately the equation connecting the energy of a photon to its frequency is just about as simple as you can get. And it's written down right here, E equals hf. So E is the energy of a photon. H is a physical constant. It's just a number, which is known as Planck's constant, named after a very famous German physicist, Max Planck. And the number in these units is quite small, 6.63 times 10 to the minus 34 joule seconds. But it's just a number. And then F here is the frequency. And so if I tell you the frequency of a particular beam of light, then you just multiply that frequency by Planck's constant, and now you immediately have the energy of the photon. So let's go back to this image of the photoelectric effect then. For the red light source, again, no matter how much we turn that dial and crank up the intensity, all that we're doing is adding more photons. Okay, more photons means more energy per second in that beam, but each individual photon still has exactly the same amount of energy, and that energy is given by this equation. We just take what's the frequency of that light, multiply it by Planck's constant, and that gives us the energy. So this allows us to understand why, in God's name, when you crank up the intensity as high as you possibly can, why can't you even get one electron to be freed from the potassium? And the answer is, all you're doing when you crank up the intensity is hitting that surface with more and more and more photons. But none of those photons have enough energy to free an electron, so you're never going to do it. And here's just sort of, we've replaced sort of the waviness, the wavy beam there with the particles here. And so it kind of just drives home again. What you're doing is you're hitting this potassium with these particles of energy. And if each particle doesn't have enough energy to free an electron, then it won't. So with that in mind, let's consider the following situation. We have two beams, not laser beams here, but two colored flashlights, one red and one blue. And we've kind of zoomed way in to where we sort of schematically are viewing the number of photons coming out of these flashlights. And we'd like to know which flashlight has a higher intensity beam. We've got one at the top, which is red and has more photons coming out per second. And then on the bottom, we have obviously a blue flashlight with fewer photons per second. So I'll pause here for 30 seconds or so to let you think about it for a second, and then we'll come back and we'll talk about it. Okay, and as always, if you're enjoying the thinking and you have more thinking to do, feel free to pause me and then come back when you're ready. So the key to analyzing this situation is, again, to remember, what does intensity mean? It means energy per second over a specific area, right? So what we're asking is, which of these beams has more energy per second coming out of that flashlight? Well, we know that the red photons have lower energy than the blue photons, right? Because red photons have longer wavelengths and lower frequencies. So remember, the equation that's relevant here is that the photon energy is equal to hf, Planck's constant, times the frequency. So a higher frequency means higher energy. So the blue photons have more energy than the red photons. But it's obvious that there are also more red photons than blue photons. So the question is, well, which wins? Okay? And the answer is, without more information and without crunching some numbers, it's impossible to tell. So it's impossible to tell. Again, if this were a physics class, we would ask exactly this kind of question, but now I would tell you, well, the red photons have a specific wavelength of 700 nanometers, which you could convert into a frequency, and the blue photons have a wavelength of maybe 450 nanometers, and you could convert that into a frequency. And then maybe if I were really sadistic, I would make you count the number of photons here and figure out, okay, which beam really has more energy. That's not the goal here. The goal here is just to drive home that photon energy is related to the frequency. Higher frequencies means more energy, and more photons means higher intensity. So that's the take home here. So now let's come back up a little bit and remind ourselves of something that I first introduced in the last lecture, which is that there are essentially three ways in which light can interact with matter. And when I say matter, I say here atoms. It's largely going to be atoms that we're concerned with. And we will sometimes talk about plasmas. Obviously, plasmas are very important in that they comprise stars. And I have stressed a couple of times, and I will continue to stress throughout the course, that plasmas are not made of atoms, right? Stars are not made of atoms. In the Earth, or in the solar atmosphere, which we'll talk more about later in the course, it does get cool enough that some atoms can exist. But in the star itself, properly speaking, in the body of the star, it's just too hot for atoms to be stable. And so the electrons and the atomic nuclei are stripped apart, and that's what a plasma is. Okay, so, but nonetheless, having reminded you of that, we're largely going to talk for the next few slides anyway about these three ways in which light can interact with matter, and we'll be often thinking about atoms. The first is that atoms can emit light, right? And we'll talk about that process. Something else they can do is they can absorb light, and we'll talk about that process. And it may or may not surprise you to learn that the emission of light and the absorption of light by atoms are very much connected. The ways in which they emit are basically the reverse of the ways in which they absorb. And so we'll talk about both of those. And then finally, matter can reflect light. And obviously we see that in terms of our observations of anything that isn't a star out in the cosmos, because stars give rise to light. There are a few other things that can give rise to their own light, if you will, as well. But certainly planets, moons, anything like that is not giving rise to its own light. It's only reflecting light. So these are the three ways that that light can interact with matter, and now we're going to talk in a little bit more detail about them. In order to understand, though, how atoms interact with light, we now need to say a little bit about what atoms are. And if it feels like you started off the semester getting excited about, or at least begrudgingly accepting, the need to learn some astronomy for the sake of completing your gen eds, and now it feels like we're getting deeper and deeper in the rabbit hole, and you're having to study more and more physics, you can't say I didn't warn you. Because again, if astronomy is the study of everything outside the Earth and how it interacts, yeah, for better or for worse, that requires a lot of different fields of study. So we started off saying, we need to understand how light works and the properties of light in order to, do our astronomy. And now we're saying, well, we also need to understand how light interacts with matter. So I guess we're going to have to know something about how matter works. So here we are with the structure of the atom. So first, let me start off with a common misconception. And I think this misconception starts in middle school or high school chemistry, maybe the first time the atoms are presented. And the misconception that I want to address first is that electrons orbit the nucleus the way that planets orbit the sun. Okay, there are lots of pictures that you'll see that look something like this, where you've got an atomic nucleus consisting of protons and neutrons, and then you've got electrons that are drawn like this with orbits around them. Okay, and it's a very sort of easy to understand picture. It's easy to remember. We have some concept of planets orbiting the sun due to gravity, and so it's easy to say, well, look, we have electrons orbiting the nucleus in a very similar way. It's just instead of gravity, it's the electrostatic force, that sort of does that. And there's a good reason that this model would be proposed, and in fact, it's what's known as the Bohr model of the atom. Bohr was a very famous, and for good reason, physicist involved in the advent of quantum mechanics, again at the turn of the 20th century. But there are some very important ways in which this model has been proven not to be correct. So, and so that's what I want to focus on right now. So this, it turns out, is not a correct model of the atom. What has replaced that model, and what is, for better or for worse, a little more complicated, a little bit more difficult to wrap our heads around, but it's important to know, is a modern quantum mechanical model of the atom. And so the picture of the nucleus is very similar. You've got an atomic nucleus which consists of protons and neutrons. But the big difference between the Bohr model of the atom and the quantum mechanical model is regarding the electrons. So the electrons don't actually orbit the nucleus in this simplistic way that was drawn at top, but instead they're located in what we could call a cloud probability that surrounds the nucleus. And at least one important aspect of this is that at any given time, there is no way to specify exactly where that electron is. All that we can say is that there is a probability that that electron can be found in some region of space. And quantum mechanics provides the formalism for a detailed specification of those probabilities. How do you calculate those probabilities? How do they depend upon the state of the atom and so on? And you can, and people do, spend entire careers on the details. It's a lot of fun. If you really want to do that, Physics 1D at Las Positas is a great opportunity to dive into quantum mechanics and do that. And if you want to know more details, you're welcome to talk to me offline as well. But the big thing that I want to stress here, obviously we're not going to be doing a lot of, or any, quantum mechanical calculations. We're not going to be diving into that math. But it is important to know that the electrons, they don't just orbit, they're located in these clouds of probability that tell us something about where the electrons are likely to be found, but never tell us exactly where they're to be found. And so graphically, the way that this is drawn in the lower left-hand corner here, for the particular atomic state that's being represented here, the darker blue means a higher probability density, which means the electron is more likely to be found in this darker region of space. And then as you go away from the atom, the sort of the intensity of that blue gets lower and lower, which is just a graphical representation of saying the probability of finding the electron there gets lower and lower. And finally, you get far enough from the nucleus and the probability is essentially zero. And so that's a way of saying, I mean, the upshot is that the electron is bound, or electrons, this happens to be a helium atom, which is drawn here, and the way that you can know is that there are 2 protons and 2 neutrons in the nucleus. But the electrons then are bound, which means they're sort of staying close to the nucleus, but exactly where they are at any given time, you just don't know. And that's one of the fundamental results of quantum mechanics. So we've mentioned several particles here, and these are things that you've probably been familiar with to some degree from prior courses, but just to cover all of our bases, I'll go ahead and define them here on the slides. So the particles that we're going to talk about, the subatomic particles that are going to be of relevance to us, are the electron, which has a negative electric charge, and again is located somewhere in this cloud of probability around the nucleus. And then the nucleus itself, which consists of 2 different types of subatomic particles. The first is a proton, which has a positive electric charge, and the second is a neutron, which is, as the name suggests, neutral and does not possess an electric charge. So for a neutral atom, and any time that I say atom, I mean a neutral atom, the number of electrons and the number of protons are equal. And so you have equal positive charges and negative charges. That means the net charge is 0, it's neutral. And that means, and that's one of the characteristics of an atom. If you either lose an electron, 1 or more electrons, or you have an extra electron, as often happens in chemistry, for example, then that's what forms ions, right? We're not going to talk very much, if at all, about ions. I may use the term occasionally, but again, since we're studying stars to a large extent in this course, it's almost all plasmas, which means that you've got nuclei and you've got electrons that are just flying around freely. They're not bound up into atoms. But here are the relevant terms, and here's sort of the terminology we're going to use moving forward. One other connection that I should make here is that the number of protons, which again for a neutral atom is equal to the number of electrons, determines the type of atom it is. In other words, if you look on the periodic table, is this hydrogen? Is it helium? Is it lithium? Is it beryllium? Is it uranium? That's totally determined by the number of protons in the nucleus. And that number is called the atomic number. The number of neutrons determines the isotope that you're referring to. So it turns out that any given type of atom can have a number of different numbers of neutrons in them, and each one of those is a different isotope. So for example, hydrogen has 3 different isotopes that exist in nature. And all of them have 1 proton because that's what makes hydrogen hydrogen. The number of protons determines the type of atom. one proton means hydrogen. The most common type of hydrogen has no neutrons at all. So the nucleus is just a single proton and that's it. And when we just say hydrogen, that's almost always what we mean. But it turns out that there are two other types of hydrogen, or isotopes of hydrogen, that exist. One is called deuterium, which has a nucleus that consists again of one proton, because it has to be a hydrogen isotope, but it also has one neutron. So this is a rare form of a hydrogen, but it does exist. It's not radioactive, so in other words, the nucleus is stable. Once this exists, it'll sit there forever until unless you destroy it in some way. And so that's called deuterium. It's just another form of hydrogen. And finally, there is a third isotope of hydrogen known as tritium, which we will talk about both deuterium and tritium, because it turns out that they are critical to the nuclear fusion that powers the stars. But tritium, as the name might suggest to you, has a proton and two neutrons in the nucleus. It is even more rare, in particular, because it is unstable, or you might call it metastable. It is radioactive. So if you just leave it to its own devices, it will radioactively decay after some period of time, on average several years. So it sits around for a while, but not forever. And each type of atom has some number of stable isotopes, just like hydrogen. So hydrogen has two stable and one metastable isotope, but lots of every other atom also has some other number of different isotopes that are stable. And so take home here is that the number of protons determines the type of atom. The number of neutrons determines what isotope or which form of that atom you're talking about. So I mentioned the periodic table. My guess is that all of you have seen this at some point in your life, likely in a chemistry class. If not then maybe in a physics class. If not then maybe on the wall of some science class you took sometime. This is it. We will periodically come back and refer to it, but it's not a chemistry class, so we're not going to be spending huge amounts of time on the periodic table. We won't be memorizing aspects of the periodic table, but it is how we organize, in a sensible way, all of the atoms in the universe. And so we will have occasion to refer to it. So here it's in the slides, so you can always refer to it. Of course, you can also just Google periodic table and find lots of examples. So now that we have our atomic terminology under our belts, let's go ahead and dive a little bit deeper and start talking about atomic structure. So we're going to start off by thinking about an isolated atom, just one atom out in space, not interacting with any other atoms. And we want to kind of understand what's the structure of that atom. Well, the key to describing the structure of an atom is in what we'll refer to as atomic energy levels. And the way that is typically drawn, or at least one way that that's sketched out, is here at left. So the E's here, E1 refers to the lowest energy state of the atom. E2 is what we will refer to as the first excited state, or the second energy state. And then E3, E4, and E5 are higher and higher energy states. Now, we stopped in this particular diagram. I stopped at E5 because I got tired of drawing lines and putting labels. It turns out that in any given atom, there are actually an infinite number of energy levels. Now, fortunately, fortunately, most of those infinite energy levels are not going to be important for us. Typically, only the lowest several energy levels are very important, but it's important to know that in principle, there are an infinite number of levels. So as I mentioned, the ground state is just another term for the lowest energy state. And it kind of makes sense if you think about, if you put a ball on a hill, that ball will roll down and eventually settle at the lowest point, right? Lowest point on the ground. And so or if you drop a ball, it'll fall until it hits the ground and then stay there. So that's kind of the way to think about this terminology. An atom left to its own devices likes to be in the ground state. But things can happen to atoms, and will, that kick it out of its ground state, if you will. And so in particular, if an atom is in its ground state, and then the way that this is drawn, this blue dot here represents an electron. If it absorbs some energy, then that electron can hop up to a higher energy state. And we call those excited states, right? In contrast, if an electron is, or if an atom is in an excited state and it gives up some energy, then that electron can fall down to a lower energy state. And that will happen as well. Something that I'm going to say over and over again, and that is critically important to what we're studying right now, is that each atom has a unique set of atomic energy levels. Okay. Hydrogen has a specific set of energy levels. Helium has a specific set of energy levels. Lithium has a specific set of energy levels, and on up to uranium on the periodic table. Every atom has a unique set of energy levels. You can think of those energy levels as a fingerprint for the atom. And that's going to be crucial because, not to telegraph too much, but one of the things that we're going to be interested in doing as we try to figure out what are these stars and what are these galaxies and things out in the cosmos made of, we're going to be trying to answer that question by finding some way to measure the atomic energy levels of the stuff that's out there. So if you want to calculate those energy levels, it turns out that for hydrogen, that's not too difficult to do. For anything else, it's quite difficult. It's described by quantum mechanics. But the good news for us is that it's a problem that has been solved. It's something that we can do. And so we know the energy levels for each atom. It's something that you can look up. And so that's something that we're not going to have to think about how do we calculate those things or how do we find those things. We know those things right now. But the biggest take home from this slide is that atoms have specific energy levels, specific atomic states, and what those states and energy levels are unique to each atom. Now, when you give an electron or an atom more energy, you increase the distance between the nucleus and the electron. So on the flip side, the ground state of an atom, which is again the lowest energy state, is one in which the electrons are closest to the nucleus, okay, as close as they can be. Anytime you give it more energy, what you're doing is you're taking one or more of those electrons farther out from the nucleus, okay? So schematically, if you look at this atom in an E4 energy state, so kind of as is sketched over here, the third excited state, the electron is farther away on average from the nucleus than in the ground state. And so the probability density might look something like this, where again, the darker blue means more likely to be there, and the lighter blue means less likely to be there, but still with some probability. If you go down to a lower energy state, the first excited state with energy E2, now you can see that the nucleus is in the same position, relatively, but the electron on average is much closer. You can see that the dark blue region is much closer to the nucleus. Even the lighter blue region is closer to the nucleus. And so we still are stuck in this probabilistic worldview where quantum mechanics doesn't tell you exactly where that particle is. It only tells you the probability that electron is in a particular region of space. But on average, you can see the electron is certainly much closer to the nucleus in E2 than it is in E4. And this is very generic. So again, as is sort of stated up here, when you give an atom or an electron more energy, it will tend to be farther away from the nucleus. And when it loses energy, it will tend to move closer to the nucleus. One of the corollaries to that statement is, if you give an electron enough energy, you can separate it completely from the atom. And in fact, we've talked about that, right? Most recently in the context of the photoelectric effect. But even before that, we've alluded to that kind of possibility when we talked about the formation of stars, or just what a star is, in the sense that it's made of plasma, not atoms. And so So the key is that you have all of these energy levels, these specific atomic states, but if you give an atom enough energy, you can actually separate that electron completely from the atom. So to sort of restate and summarize some of what we just said, when an atom absorbs a photon, gains energy, the electron jumps up to a higher energy level. The atom is excited now, the electron is farther away on average from the nucleus, and it's at a higher energy. And so if we draw the probability distributions again, you have a low energy state atom which absorbs a photon, and that's what this, when you see these squiggly lines, that just means it's a photon coming in. So you have a particle of light, it gets absorbed by the atom, and then that atom jumps up to a higher energy state. Okay, and what that means is the electron on average will be farther away from the nucleus, and so the probability distribution here is expanded. And in terms of an energy diagram, you'll see something like we have here at right, where energy always increases upward, and we have these two different energy states. But the opposite situation can also occur. When an atom emits a photon, it spits it out, the electron has to fall down to a lower energy level, and the probability density of that electron shrinks as the electron moves closer to the nucleus. So it's exactly just the reverse of the prior slide, where you start off with an atom in a higher energy state, where the electron is a little bit farther away from the nucleus on average. That atom then decays, which is the word that we use to just mean that it falls down from a higher energy state to a lower energy state. When it does that, that energy has to go somewhere, and what it does is it goes off in the form of a photon, in the form of a particle of light. And so that light goes off, and it leaves the atom in a lower energy state, where those electrons, again on average, are closer to the nucleus. Now, one piece of information that's absolutely critically important here is to know that the energy of that photon that gets sent off into space is exactly equal to the difference in the energy levels of the atom. Okay? And that might be obvious to you, but it might not. And in either case, it's worth stating a couple of times. This is, if you want to be really fancy, you can say this is an example of conservation of energy. Which is just a way of saying that energy in nature, we believe this to be a law of nature, is that energy is neither created nor destroyed. It's just converted from one form to another. And so in the initial state, you just had a high energy state atom. So the atom itself was in a higher energy state. When it decayed to a lower energy state, it had to give up that extra energy. That extra energy had to go somewhere. It couldn't just be destroyed. And so the form in which that extra energy was gotten rid of, was emitted, was in the form of a photon. And so again, we're not going to be crunching numbers in this context, but it is important to know that the energy of that photon is just equal to E2 minus E1. So in other words, how much energy did the atom start with? How much energy did the atom end up with? What was that difference? That's the amount of energy that has to be carried away by the photon. And similarly, that's exactly the amount of energy that you would need to give in to the system in the form of a photon if you wanted to excite an atom from E1 up to E2. So you can excite an atom with a photon by having it absorb a photon, or if it decays, it will emit a photon of exactly the same energy. It's also important to know that atoms, at the risk of anthropomorphizing atoms, atoms don't like to stay in an excited state, or to not anthropomorphize an atom. They don't stay in an excited state very long. And the more excited the state is, the higher the energy state is, the shorter amount of time that it will stay there in general. And so the upshot is that once an atom is excited, it will almost immediately emit a photon. Just think about it, as fast as it can, it's going to give up that extra energy in the form of a photon and then decay back down to its ground state. So how do we relate the energy of a photon to its wavelength? Because I've made allusions to this connection several times. And so I want to make it concrete now. So a couple of equations that we've seen, one of which earlier in this lecture, and then one a few lectures, maybe just in the last lecture actually. But so the first is that we can relate a photon energy to its frequency using this equation at left, E equals HF. Meanwhile, but that connects the energy to the frequency, not to the wavelength, right? So we know if I give you the frequency, you know how to calculate the energy of a photon, but what if I give you the wavelength? Well, the key to that connection is to recognize that there's a fundamental connection between the wavelength of a photon and its frequency. And that's provided by the second equation here at right, C equals lambda F. So if you remember, this is an equation that is almost true for any wave at all, whether it's light or water or sound or any kind of wave you can think of. The speed of a wave is always equal to the product of the wavelength and the frequency, which just means you multiply the wavelength by the frequency, the result is the speed of the wave. The only difference here is that the speed of light is always the same. It's the speed of light. We label that c. And so if you give me the wavelength, I can give you the frequency. And so now that we have a connection between the energy and the frequency, and also a connection between the wavelength and the frequency, we can combine these to get a connection, to get an equation that connects the energy of a photon with its wavelength. So, and it's a two-step process. If you'd like algebra, here are the details. You solve for the frequency in terms of the wavelength, and then you substitute that into the equation for a photon energy. And so the result is that the energy of a photon can be written as h times c, the speed of light, divided by the wavelength. So now let's take things up a stage, if you will, up a notch. So far we've been talking about everything in terms of a single isolated atom. So, which is how physicists always start off. You always start as simple as possible because things will get complicated soon enough. So, but we understand now how one atom works. It has a specific set of energy levels, which are unique to that atom. And then if you hit it with a photon, you can excite it to another state. And once it's there, it doesn't like being excited, and so it will tend to fall down to the ground state again and give up that photon. But now let's imagine what happens when we have a cloud of many excited atoms. So not just one atom, but we have a cloud of atoms now. And so let's imagine this is a hot cloud, and it needs to be hot because we want excited atoms. So, you know, we could talk in a whole lot more detail, and again, in a physics class we would, but the ground state is the lowest energy state. If the gas is cold, then essentially all of the atoms will be in their ground state or very near it. If you want to have a lot of excited atoms, you need to be hot. So we've got a hot cloud here, and we're gonna talk about something that is hypothetical, but is a good approximation for us, which is what we'll call here two-state atoms. So I told you already that atoms have an infinite number of states, but I also told you that for practical purposes, most of those states are irrelevant, and only the lowest energy states are typically very important. And so we're going to cut that off and just consider two states. So we've got a ground state E1, and we've got some excited state E2. So what kind of things are going to happen here? Well, if we've got a hot cloud with many two-state atoms that are excited, well, those excited atoms are going, we've already said excited atoms don't like to stay excited, and so pretty quickly they're going to fall down, decay to the ground state, and they're going to, in doing so, they need to emit a photon whose energy carries away the extra energy, right? So if the atom is going from E2 down to E1, it has to emit a photon whose energy is equal to E2 minus E1, okay? So all of these emitted photons are going to have the same energy, E2 minus E1, because all of these atoms are the same type of atom. If you want to be concrete, imagine this is a cloud of hydrogen gas. As it turns out in astronomy, most clouds are hydrogen gas. But this would be true of any kind of gas. But also importantly, the photons are going to be emitted in random directions. And so if you have a cloud of a lot of atoms, that again is hot, and so things are being excited, and then those excited atoms are decaying, it's going to be emitting lots of these photons with energy E2 minus E1 in all directions. So now let's imagine this is happening out in space, and it turns out that this is not just your imagination. This actually does happen. But we're stuck on Earth, which is also not your imagination. That actually happens too. So we're stuck on Earth looking up into the sky and trying to capture whatever light we can. And so it turns out there's a hot cloud of gas out there somewhere in the universe, and it's emitting some light, and some of that light gets to us. Well, we're clever enough to set up a telescope and look at it. And so we collect some of this light that has traveled, some untold light years to Earth. And then, to sort of refine it and make a very nice and detailed observation, we're going to pass it through, we're going to collimate it, we're going to pass it through a slit, we're going to pass that slit through a prism. And if you're wondering why a prism, it's because we want to separate out any different colors, if there are different colors. Now, in this particular case, there aren't. You can see we've said this is a two-state atom, and so all of the photons have exactly the same energy, which means exactly the same frequency, which means exactly the same color. That's why they're all green. And so we pass that through a prism, and that just bends the green light. There's nothing else to separate it. But then we finally put a piece of black paper on the back of our apparatus, and we look at the projection. And what we see is a line of green light that corresponds to a very specific wavelength. So again, sometimes I'll say color, sometimes I'll say frequency, sometimes I'll say wavelength, but to a physicist or an astronomer, these are interchangeable. They're different things, but if you know one, you know the other. Okay, and so we find a very specific wavelength then that corresponds to the energy of the photon that was emitted from this cloud. Now, I told you a few slides ago that each atom has a unique set of atomic states. And so here's a particular diagram of the atomic states or the energy levels of hydrogen. And so you see it can look a little complicated, but it really isn't too bad. And so the ground state is here at the bottom. It's the lowest energy state of hydrogen. And then if you go up to the first excited state, labeled here by 2, you've got a different state. And here the energies are listed here. The energies happen to be negative, and that's by convention, because by convention, it's agreed upon that an energy of 0 when describing an atom means that you have separated the electron from the nucleus by a distance of infinity. So the idea is if you have a nucleus and an electron that are infinitely far away, then there's no energy of interaction. And so as a result, any bound state of that atom, any stable atomic state, will actually have a negative energy. But don't let that hang you up. So we've got lots of states here, because as I said, hydrogen, just like every other atom, in principle has an infinite number of energy states. And so here on the left, you've got labels of those states. So 1 corresponds to the ground state, 2 corresponds to the first excited state, 3 corresponds to the second excited state, and so on. Now, what you'll notice first here is that as you get to higher and higher energy levels, these states get closer and closer together. Okay, so that's first thing that I'll point out. The second is that, as we discussed in detail in the last slide, it's when atoms undergo transitions, the photons, so decay, let's focus on decays in particular. When an atom decays from an excited state down to a lower state, whether it's the ground state or not, it has to give up that extra energy in the form of a photon. Okay, and that's what's being represented by these down arrows that are drawn, in these 3 sets. So this first set of arrows, which is what's known as the Lyman series, it represents transitions down to the ground state. So you can see all of these arrows end on the ground state. Where they differ is where they start. So this arrow at left is an atomic transition where the atom started in the first excited state, this, number 2, the second state, which is the first excited state, and then it decayed down to the ground state. So if it does that, it's going to emit a photon whose energy is equal to E2, this number, minus E1, this number. Or you could have an atom that starts in the second excited state, which is number 3 here. If it decays all the way down to the ground state, it's going to emit a photon whose energy is equal to E3, which is negative 1.51, minus E1, negative 13.6. And similarly for 4, 5, 6, and of course you could decay down to the ground state from any one of these infinite number of energy states. And so in this diagram we sort of cut it off at 6, because at that point you can't draw an infinite number of lines, so you've got to pick a place to stop. But the point is that what's called the Lyman series here is the set of all transitions that end in the ground state. Okay. Now it turns out that each one of these has a particular energy, as I've said, and so you can calculate, well, what is the energy difference between E2 and E1, and what wavelength or what frequency does that photon have? Okay, and you can do that for all of these transitions. Now it turns out for the Lyman series, all of those transitions have wavelengths or frequencies which put them in the ultraviolet range. So these are invisible transitions. So if you had a cloud of hot hydrogen gas that was making these transitions down to the ground state, you wouldn't see any of them visibly. Of course, we have telescopes and technology capable of measuring them now, but you wouldn't see them visually. Having said that, there's another set of transitions known as the Balmer series, which you would see. And the big difference between the Lyman series and the Balmer series, as this diagram indicates, is that instead of decaying down to the ground state, the Balmer series consists of the atomic transitions which end at the first excited state. So you don't come all the way down to the ground state, you stop at the first excited state here, and then you look at the transitions that end there. And so if you come from state number 3 to state number 2, for example, that transition gives you a photon that happens to be red. And if you come from the 4th state to the 2nd state, that gives you a transition that is green. And if you start in the 5th state and you come down to the 2nd state, then it turns out that gives you a photon that's blue, and so on. So the Balmer series is a very important series because that's actually in the visible range. That's something that you can see physically. And so this is an experiment that's relatively easy to do in the lab. And again, when I've taught Astro 30L at Las Positas, this is a lab that I have done. And it's something that's done in physics classes as well. You can get a tube of hydrogen gas. You can use an electric current to excite it. And when you do that, it will emit light. And that light is largely red. It turns out it's a characteristic red color. And that's because of the dominance of this 3 to 2 transition here in the Balmer series. And there's yet another series known as the Paschen series, which ends on, which decays. Instead of ending on the ground state or the first excited state, it decays down to the third state or the second excited state. And all of those transitions, it turns out, are in the infrared. So none of those are visible. These photons have too little energy to be in the visible range. So the Paschen series is too low energy. The Lyman series is too high energy. But the Balmer series, those transitions that's the Goldilocks series, if you will, just happens to have a number of transitions which are in the visible range and which we can see. And so this is by far the most detailed analysis we're going to do of any set of atomic transitions. But it's important because it kind of puts all of everything together that we've mentioned over the last several slides. Hydrogen, just like every other atom, has a specific set of atomic transitions. And those atomic transitions give you very specific colors, very specific wavelengths of photons. And we're going to be able to use observations of those wavelengths to identify where hydrogen is in the universe. Okay, and that's kind of, if you remember nothing else, I hope you remember a few other things, but if you remember nothing else from this lecture, this is the most important thing, which is that as astronomers, we are able to determine the composition of stuff out there. What are the stars made of? What are the planets made of? You know, what are things made of based upon the light that gets to us? And this is one of the most useful tools for actually doing that. You look at the wavelengths of the light that get to you, and you say, okay, what type of atomic transitions could give rise to that? And that allows you to figure out, using, again, this kind of virtual fingerprint, what type of things are there. And this is just kind of a sketch that shows in a little more detail, if you were to do this experiment, what you would want. You know, I described that this is something that we've done at Las Positas. You take what's called a gas discharge tube, which just means a tube, you know, with this gas inside it, that you use electric discharge. You apply a voltage across it in order to excite those electrons, and then, or excite the atoms, and then when the atoms decay, they emit light. That light can be passed through a prism, and in general, there will be several different wavelengths that will come out, because there will be several different transitions that will be occurring, right? A few slides ago, I had a very simple two-state atom where there was just one transition that was happening, and that means there's only one color photon that's coming out, and then you have one line on your black screen here, okay? But in reality, atoms have an infinite number of atomic states, and so all of these transitions will happen, some of them more frequently than others. So, you know, some of these lines will be brighter than others, certainly, and some will be so faint that you won't even see them. But you will almost always have multiple lines, and that's actually good because that makes your fingerprint even better, right? So each atom will have a specific set of visible lines or visible wavelengths that are emitted during these transitions, and we can use those transitions to figure out what is this atom. And so here are just, you know, I've said several times now that each atom has its own unique set of atomic states. Now, you know, using the process that we've described in the last few slides, we can use that to also conclude that each atom has its own unique signature of what we call spectral lines, which just looks like this, and is constructed using the process that was described in the last slide. So if you take hydrogen gas, put it in a discharge tube, and then separate out the colors that come out, you get something like this. You get this strong red line that comes from the Palmer series, the 3 to 2 transition, we would say, from the third energy state down to the second energy state. But then you have a number of other lines as well. Helium has a different set of lines. Neon has a different set of lines. So we refer to these as lines because they look like lines. The way that, you know, based upon the way that we do the experiment and the way that we project the light out of the prism onto the screen. But the important thing is that each of these lines has a particular wavelength. Long wavelengths are at the right, short wavelengths are at the left. And so, you know, if we were doing this in a detailed way, we could put a label up here at the top that says this goes from, say, 400 nanometers here at the red end to 750 nanometers or something. Sorry, it would be the other way around. 750 nanometers at the red end, 400 nanometers or something at the purple end, and we could just read off for any particular element at what wavelengths do those lines exist. And so if you have a gas that you don't know, you want to know, what's in this discharge tube, and you don't know, or more exciting, there's some, cloud of gas that's giving off some light, that you're capturing with your telescope, and you want to know what's the composition of that gas. Well, you collect that light, you pass it through a collimator, pass it through a slit, pass it through a prism, you look at the set of spectral lines that come out, and you compare it to the signatures that you know. And then you just start checking things off. You say, yep, it's got the hydrogen lines. Yep, it's got the helium lines. No, it doesn't have any of the sodium lines, and so on. And so in that way, you can determine what is the stuff out there made of? Pretty cool. So now we're deep in the business of what we call spectra, right? A spectrum is just a set of wavelengths, or a set of frequencies, or a set of colors, right? And it turns out there are a few different types of spectra that are going to be useful for us to refer to. So the first is what's known as a continuous spectrum. And that's something that's produced by just a hot source. So if you look at a light bulb, for example, it produces white light, which is a combination of all colors, all wavelengths. And so if you pass that through a prism, you're going to get a continuous band of lines. And so they don't look like lines, it's just a continuous spectrum. And that's what's drawn up here at the top. A second type of spectrum is created by a hot gas. And this is what we just spent some time talking about. So a hot gas gives off only specific wavelengths because it has only specific atomic energy levels, and transitions between those levels are what give rise to these wavelengths. And so a hot gas will send off photons with particular energies or particular colors. If we pass that through a prism, we will get specific lines. And so instead of the continuous spectrum that was given off by just a light bulb, for example, we will get what we refer to, not very creatively, as an emission line spectrum. Emission because the hot gas is emitting this light. Line because it's giving rise to specific lines. And spectrum because it's a spectrum. The third type of spectrum that we're going to be interested in is something that's generated that kind of takes two parts. It's the result of a continuous spectrum passing through a cool gas. Okay. So in this case, what happens is the white source here, the light bulb, if you will, gives off a continuous spectrum, and that continuous spectrum passes through the cool gas. So what's going to happen when that occurs? Well, in order for an atom to be excited, so first let's say this is a cool gas, so the atoms are mostly in their ground states. Now, in order to excite an atom from its ground state to an excited state, it has to absorb a photon. But not just any photon will do. That photon has to have exactly the right amount of energy to take it from the ground state to that particular excited state. Now, it has a number of options. It can go to the first excited state, it can go to the second excited state, it can go to the third excited state, and so on. But it can't go in between. So there are only a specific set of photon energies that can be absorbed. The result is that most wavelengths, most photons, pass straight through that cool gas and come straight to us. But a select few, those specific photons which correspond to atomic transitions in that cool gas cloud, will be absorbed. The result is that what finally gets to our eyes here on Earth is what we refer to as an absorption line spectrum, where it's mostly a continuous spectrum, but then there are a few dark bands where those photons got stolen, if you will. They got absorbed by that cool gas, and so they didn't get to us. So now that we know the three main types of spectra, I want to say a word about how I will represent these spectra. And there are a couple of different ways, but one very common way is to plot the intensity on the vertical axis as a function of wavelength on the horizontal axis. And so if we do this, what we're saying is how much of a particular wavelength, what's the intensity of a particular wavelength that we're observing here on Earth, for example. And so a continuous spectrum has a curve that looks very much like this. So, on the left end is the high energy end. This is purple or even ultraviolet here. So the farther you go to the left, the more energy a photon has. And so it'll always start at zero eventually, because zero wavelength would mean an infinitely energetic photon. And so we won't have any of those because there's not an infinite amount of energy in the universe. So the curve will always start at zero, but then it will come up, it will peak somewhere, Where it peaks, what the wavelength of this peak is actually going to be something that we're quite interested in, and it'll tell us a lot about the star that we're looking at. But then it'll tail off, in this way. So this is kind of going to be we'll become very familiar with this type of curve. It's a characteristic intensity curve of a continuous spectrum. In contrast, an emission line spectrum looks quite a bit different, right? For an emission line spectrum, most wavelengths have nothing, right? There are only a specific number of wavelengths that have any energy being emitted. And so it'll be lots of zeros and then these isolated blips or peaks where you have quite a bit of energy at a particular wavelength. And so you have two lines, and so you have these two peaks very near one another. And then there's a dark region where no energy is being emitted, and so you have zeros, and then another peak, and so on. And so this is what an emission line spectrum and a continuous line, or and a continuous spectrum would look like plotted in this way. Now, this one is something that we're going to see several times, which is the actual spectrum of a star. So far I've laid things out, in a relatively, I don't want to say relatively simplistic, because there's been a lot of information here, and so particularly if these concepts are new, it's not something that I would necessarily call simple, but they've been idealized. Okay, when we look at a star, which again is what we're really interested in at the end of the day, the details look a little bit messier, and so this is a typical spectrum of a star, which is, as it turns out, a combination of both a continuous and an absorption line spectrum. And so you can see if you sort of ignore these, what's labeled absorption line, not to sort of play spoiler here, but if you ignore these absorption lines, you can see that you kind of could trace out something that looks at least kind of like what I claimed a continuous spectrum looks like, where it starts out zero intensity. Here I've labeled it brightness, but that's just another word for intensity. Starts out very low, then it rises, it peaks, and then it falls off. So the spectrum of a star looks a lot like a continuous spectrum, but then there are some features here which are very different, which again are labeled absorption lines, where the brightness coming through at that particular wavelength is much lower than you would expect, or much lower than it would be for a true continuous spectrum. And so the question is, why would that be? Where did those photons go? Well, as the label here, absorption line, suggests, something is absorbing that light. So it could be, and it turns out it could be two things, maybe more than two, but there are two particular things that it very often is. One is that if this is a distant star, there could be a cloud, maybe even multiple clouds, of cool gas in between that star and us, which is absorbing some of those wavelengths. Okay, and so if that's the case, then these particular wavelengths could be useful for determining what is that cool gas made of. Okay, the other thing that it could be, and this certainly does occur, is that, as I mentioned a few times, in the upper atmosphere of stars, it actually does get cool enough for some stable atoms to exist. And so in that case, as the light leaves the star and passes through its atmosphere, the atoms in its own atmosphere will absorb some of those wavelengths, blocking them from getting to us. So if you look at the sun, and I will explicitly show you the sun's spectrum as well, but if you look at the sun spectrum, there are some absorption lines there. And it's not because there's cool gas between the sun and us. There sort of is, but that cool gas is actually in the upper atmosphere of the sun itself. And so you could actually figure out something about what's the composition of the sun's atmosphere just by looking at what the absorption lines in the sun spectrum are. And just to sort of give you a sense of how useful this information actually is, there's a whole lot that we can squeeze out of this. Remember that the game of astronomy is to squeeze as much information as possible out of the light that we get. Turns out we can squeeze a lot out of a spectrum. So by measuring the strength of the absorption lines, which is just a fancy way of saying how deep this falls, how big the drop in the brightness, astronomers can tell how much of each atom there is in the star. And moreover, we can determine the temperature, the pressure, and the density of the region in the star that contains that atom. So it's really pretty phenomenal. I mean, it seems kind of like magic. It's not. It's physics. But we really can determine a whole lot about objects just by looking at the light that we receive from them. So, here we are back to the periodic table. And now it looks a little bit different, and it's kind of odd looking, but now it's colored in a way that we'll come back to a few times, because what we're interested in is, where do these atoms come from? Okay. When we look at the spectrum of stars, we only see certain elements. Okay. So it turns out that now that we're experts in analyzing spectra, and now that we know that each atom has its own unique set of spectral lines, we can start looking at every star that we can see and then breaking up its light into its spectral lines and determining, okay, what is this star made of? Well, it turns out that when we do that, we only see certain elements, and these elements that are highlighted here comprise 99.999% of the sun. Okay, I've mentioned before, and I'll say again, the sun is a very garden variety star. It's a very sort of just standard, plain vanilla star, which is in a lot of ways very useful for us, because it means that by studying the sun, which is easier to study than anything else, any other star certainly, we can actually learn a lot about just average stars of the universe. And it turns out that 99.999% of the sun is these highlighted atoms. So hydrogen, helium, carbon, nitrogen, oxygen, neon, and sulfur. Okay. Well, that's cool if you're wanting to describe the sun. You say, well, okay, I guess that 7 elements, will give me almost all of the sun. But what on earth is where are all the other elements? So we'll talk about that as the semester goes on. One of the things that we'll be interested in actually is where did all of the elements come from? Like, where did these, how do we produce these things? And where do we find them? A lot of that information is going to come from spectra. And so I thought that it would be fitting to end this lecture by showing you a full spectrum of the sun, which is pretty daunting. I'll be honest. I mentioned that so far most of what we've talked about, certainly in this lecture, has been fairly idealized. The details of reality are messy, and this gives you a sense of just how messy it is. So that's good news if you want to be if you're interested in being a professional astronomer or astrophysicist. There are still some jobs to be had. There's still work to be done, because there's a lot of complexity out there. Fortunately, I can promise you I will never be giving you a test question which gives you an image like this and says analyze this. But the point is that you can see that there's a largely continuous spectrum being emitted from the sun. You can see you've got purple wavelengths all the way up to reds, but there are a whole lot of missing things too, right? A whole lot of absorption lines that are where these photons have been taken out by something, and what that something is well, a lot of different things, right? Different elements in the sun's upper atmosphere, and then each one of those elements has lots of different atomic transitions, right? An infinite number in principle. In practice, in the visible spectrum anyway, it's not an infinite number of transitions, but it's a lot. So again, the take home is the details are messy. We're not going to be nearly this messy in the majority of this class, but at least you can tell your friends you've now seen the full spectrum of the sun. So thanks for your attention here today. I hope that I've convinced you that in addition to being a wave, or behaving like a wave, light also behaves like a particle, and hopefully impressed upon you the importance of spectra to our study of stars. We're going to do a lot more with this going forward, but until next time, have a good evening.